talk about serialization and a bit object graph communication. My name is Florian. I'm one of the co-founders of the Microservices project, and today I will show common pitfalls or security issues about the serialization itself, and why we decided to develop a new serialization framework from scratch for our storage engine, and what the benefits are. First of all, a bit legal stuff I have to show. And then what is serialization? How does it work? So in a nutshell, it's conversion from an object graph to a binary representation or a transport table format. Most commonly used is a byte format or JSON or XML or something which can be sent over wire or stored in a binary store. And on the other side, the deserialization process creates Java objects out of these transported data again. And that's basically serialization. So yeah, most common use cases, of course, is to transport the data over a network, to put it in a cache if you want to store by value and get copies out of the cache, or to just store data on some binary store, the hard disk or cloud drive or whatever. So where is it used? In short, almost everywhere, in every application. Most application developers use serialization without knowing it, because the caches or frameworks use it internally. If you have a web framework, the data which is cached in a user session, for example, is serialized in some sort of a hash table or key value stores. It's used in every type of stream processing, like a Kafka, or in distributed caches and grids, like Hazelcast, for example. In remote method invocation has to work with serializations. All application servers use it internally. And of course, if you are working with web and REST services, if you put a payload of objects into an HTTP call as an answer, it's mostly serialized as a JSON in a JSON format, and that's called serialization as well. So yeah. Without knowing it, everybody is using it, and no one makes or does think too much about it, because it just works, and the frameworks take care of it. But if we look behind the scenes, serialization is a bigger issue than most of us think. If you look at the quote of Mark Reinhold, he said serialization was a horrible mistake because most of the security vulnerabilities in the Java platform itself are linked to the current serialization in the JDK, and that's my key point. If I say serialization, I basically refer to the built-in serialization in the JDK, not a JSON serializer or whatever frameworks are out there, but the Java serialization itself, which is built in the JDK and used by the JDK heavily. So they have a lot of conceptual issues from the beginning, and to keep the backward compatibility of the JDK, they couldn't fix it. So it's an ongoing text, like Brian Kett said, and not only for the JDK maintenance, but also for library maintenance as well, and all the users of it. If you look at the CVE details, where security lags are monitored all over the globe, you can look it up at the CVE details.org or at JODN. Back then, the data is a few weeks old. There were over 2,000 critical vulnerabilities, and most of them are linked to the Java serialization. And the most known, I guess, was the struts vulnerability. A lot of servers were attackable and have been attacked. And happily, the Struts team fixed it quickly, and most of the servers could be patched, but it was a heavy leak. A lot of data got lost, a lot of money got stolen, and that's all because of a simple bug in a serialization. A lot of other libraries have inherited the problems, like the Apache Commons collection, which is used heavily in a lot of frameworks, and they have to fix or circumvent these bugs all over. So what are the vulnerabilities? All serializable classes on a class path can be serialized. So if you pull in libraries with classes you don't even use or you don't even know, libraries have dependencies as well. So you pull in a lot of other dependencies with classes you don't even know or use, can be serialized. And if there are bugs or security issues with these classes, they can be injected and can cause problems. So yeah, that's the second point. The injecting of malicious code is scarily easy. Stephen Poole has a demo on his talks on various conferences. There are YouTube videos online as well. You can look it up. He demonstrates it live, how easy it is to inject malicious code into a serializable stream and into running applications. Yeah. So nowadays, they added a bit of protection, like black and white listing. Thing is, you have to do it. You have to know what classes should be serialized. You probably don't know, because dependencies, what classes are used, you never know. So nobody does it. And yeah, like I said, most of the dependencies use it anyway, and you never know what classes are involved in a serialization. If you forgot to whitelist it, it crashes. Yeah, good luck with that. So these are the vulnerabilities. They are well known, and it has a lot of limitations as well, of course. You have to implement the Java.io serializable interface in order to serialize classes. That's a problem if you use third-party libraries or objects from classes from third-party libraries which you want to serialize, but they don't implement serializable. You can't do it, so you're lost there. And serializable API doesn't have an API contract. It's just magic methods. It's an empty interface with no methods. You have this old obsolete serial version UID with a magic number in it, and if you want to customize how a object is serialized or deserialized, there are some private static methods, I guess, in an object you have to override. Yeah, no API contract, magic stuff, not really good testable. Yeah, not very well designed. So that's, yeah, could be done better. So, and next thing is, after the deserialization, you always get an object copy, of course. So if you have a live object graph on one side and you want to transfer data or update this object graph partially, for example, you have to do it by yourself, by hand. Meaning you have to know where to put the objects in a graph on the right point and so on. Probably not really used for cases like this. So it's hard to keep two graphs synchronously. Maybe if you want to replicate two nodes in memory, you have to use different frameworks to do that. Doing that by hand is really hard with our current serialization techniques. Yeah. So what are the current alternatives? There are a lot of frameworks out there, of course. A lot of them are bytecode based, like Creo, for example, but most of them make the same conceptual mistakes, and they do a lot of stack-based recursion, meaning the depth of a graph is limited. Cyclic references are a problem, or changes in the classes cannot be really reflected. So if you update one node and have an older version on another node, the transformation of the data is hard to do. And on the other side, you have the human readable formats like XML and JSON. But JSON is heavily used in REST, for example. It's easy to use because it's human readable, of course, but it's a needless overhead for machines. Machines don't need human readable stuff. The parsing is needed. It's more processor power is used, of course. The data gets bigger, so more traffic. And it's only really suited for not very complex data, flat lists and stuff like that, because if the format itself, of course, has limits. It's a tree format, JSON and XML, and not a graph format. So if you have cyclic references, it cannot be done with JSON or XML. And if you have multiple objects which are referenced multiple times, they always put copies of the data in a JSON code. So it blows up very fast. It's not really suited for complex data, but for simple REST calls which deliver lists of some sort, it's fine. Yeah. So we see we have the bytecode-based frameworks with limitations to human readable stuff, with limitations as well. So you can say you have to decide on the use case, of course, what framework you use, but we have to live with limitations. In a JDK, there's a proposal by Brian Götz towards a better serialization. It is 4 years old. It's from 2019. The details can be looked up at the Ember project site. And it's a request for a better serialization implementation in a JDK, or more of a specification, but they don't want to implement it. They leave the implementation for third-party vendors. And but this proposal still has conceptual issues. It still breaks the referential integrity at the deserialization. It still violates separation of concerns, because you have to, if you want to customize how the serialization is done, you have to put it in your business model again, so it's not separated. And like I said, it's only a draft for an API spec and not for an implementation. So if it really comes in a JDK, we have to wait again for vendors to provide an implementation, and it's not in a standard. Yeah, we'll see. And in a Microservices project, we had the problem: what do we do? We use serialization very heavily for the storage manager or the object storage, and so we saw that Java serialization wasn't the solution for us, and the other framework providers as well. So because of that, we decided to develop a new serialization from ground up, designed to eliminate these shortcomings of the existing ones. And the serialization engine is optimized for security, of course, flexibility and performance. And it's heavily used in all our modules, in a persistence layer, in a storage layer, in object graph communication, and in the cache. By the way, these projects are all open source, and we are moving it to the Eclipse Foundation, and we will build a standard out of it. We will propose a standard for these techniques, so it can be used and adopted in different frameworks as well, but more to that later on. Key points were, of course, the separation of data and metadata. That's a security issue, or prevents the possibility to decrypt the data easily, because we don't send the metadata or the description of the data over the wire like the JDK serialization does. And no code is executed at deserialization. That's the most common door for attacks. When objects got deserialized in memory, code is executed, and that's where most malicious code can be injected, of course, and executed, and we don't do that as well. So injecting malicious code is technically impossible. Even if you have attacking code in your objects, it can be executed. And we keep the referential integrity. because we use an internal technique called swizzling, which is a mapping from object instances to IDs, which is a long, so basically unlimited amount of objects. And we can keep the state of subgraphs over several machines. So we can reconstruct parts of object graphs and sync different nodes, and you don't have to worry about merging the incoming data into an existing graph. That can be done with a serializer. All right. So how does it work? First of all, of course, you have the serializer has to analyze how the objects are built up. It's done by reflection, of course, and a metadata layer is created. So in a life cycle of an application, this analysis has to be done only once and can be cached in a JVM. And only if new classes are discovered in a serialization process, this metadata creation has to be run again. But the serialization has gotten pretty quick, so you don't have to worry about performance there. And if the serialization engine detects a change in classes, so if you have a existing data of serialized, you have existing serialization data, and the engine discovers that the class has changed compared to the existing data, a type mapping can be done, so you can convert older data to, or map older data to newer classes. The engine can cover the most common cases, of course, if you rename fields or move fields and stuff like that. That can be done automatically, but if you have more complex cases, for example, you split a field, you have a field called name and split it into first and last name, then you have to provide a custom mapping or conversion. But you can navigate your data through the evolution of a software, changes of types, of course. At the deserialization process, it works in the following way. The data which comes in is put off heap. That's the reason, because we don't want to trouble the garbage collector too much. Then the objects are created. Only the shells of the object are reserved in memory, and the addresses are assigned to these objects. Then the fields are populated, and afterwards the linking phase comes and restores the referential integrity of subgraphs or bigger graphs. So the depth of the graph doesn't matter, or if you have referential, if you have cyclic references, it can all be handled by the machine. And this is, of course, without any, we call it monkey business or magic code. We don't use bytecode manipulation of any sort, or any injections in a JDK, instrumentation, stuff like that. It's just pure Java code, which uses performance optimized memory handling with direct memory access depending on the operating system. And that's the most quick and secure way to restore the objects in memory. So, and of course no code is executed at deserialization. So the limitations of other frameworks we've seen or decided it's important for us. We managed to eliminate it, so any object can be serialized. There is no need for the serialization engine to your classes don't have to implement the Java IO serializable. There are no superclasses or annotations of any sort needed. Just use the pochos as they are. They can be serialized. You can use objects from third-party libraries without a serialization interface, serializable interface, and the separation of concerns was a big point for us. So you don't have to put magic methods in your business logic or in your pochos in order to customize the serialization or how the bytes are represented. You can do it with external handlers. So you can customize the serialization for third-party libraries as well, because you don't own the code. You can't inject code in the Java util ArrayList, for example. So you have to use it external handler, and it's on separation of concern. You don't have a technical detail in your business code. The depth of the object graph is not limited because we don't use stack-based recursion, and like I said, the class changes can be covered through technical we call legacy type mapping, so a mapping from older versions to newer versions, basically. Yeah. We did a bit performance check with about 100,000 objects. The Java Serializer, which is optimized actually for a compact format, but not for performance, takes over 1 second. Even the JSON or XML serializers are faster, which have a very huge amount of data. The data is 10 or 20 times bigger than the byte format of a Java serializer, but they are even quicker. So, and the Microservices serializer has a very compact format as well. But since we're doing pretty much the same layout as the JVM does in memory, we don't have to do a lot of mapping and conversion. So the performance is the quickest way possible. So it's pretty much dependent on the hardware you use. Only bytes are transferred from A to B, and no conversion is happening in any way. Okay. Benefits, of course, it's easy to use, pure Java, no external dependencies. There's no internal configuration, so no mix-up between technical code and business logic. You don't have to update your classes or to decorate your classes, just to serialize them. And it fits seamlessly into the object model, of course, and the separation of concerns. It's highly secure. It's in our eyes, the fastest way possible to serialize classes. And the library is open source and available in Maven Central. It's in a persistence binary module, currently in the version 8.1, and the API is pretty simple. It's just a serializer class. Let me check my laser pointer here. Yeah, it's a serializer and a transport format. Most of the time it will be just a byte array. You can use byte buffers or whatever transport format you like. You can re-implement the serialization process. What we are offering are bytes and byte buffers for on-heap and off-heap conversion. And a serialize method just creates a byte, and the deserialize restores your objects, and that's basically it. The API you will use most of the time. It can be heavily customized, of course. The complete API is interface based, so you can exchange every simple part of the engine and customize it on demand, or write custom type handlers, of course, if you want to optimize how an object is converted to bytes and back. And this is done with custom type handlers. You can take control over the storing and loading or serialization and deserialization of specific Java types. You register one type handler for one specific type. Let's say you have a custom pojo which is heavily used in your application, and you want to optimize the data transfer of it because you're pulling millions of objects over the wire every minute. Then if you can save a few bytes in these objects or get it down by half, it's a win over the long run, of course. The example I will show is a simple time slot class. You have a slot number and a start and end date, for example, and the serializer, the serialization engine, has built-in type handlers for the most used JDK types, for all collections, for the common types which are always used in business logic, we provide special type handlers, but if the engine detects new types, mostly user-written code, it has to generate generic handlers, and the generic handlers say the timeslot class are basically 3 objects. You have the timeslot type itself, and the 2 dates or references as well. And in order to keep the referential integrity intact, the serializer creates 3 records by default. So this is good if you say referential integrity is important. Most of the time it is, of course, but if you have simple value types like dates or local date or strings, you can inline the date in the original record and strip the 2 date records out of the data set. So basically the generically generated type handlers look at the fields. Primitives are written directly in a record, and references are converted or mapped to an internal ID, like here, and referenced by the object ID in the record itself. So every record in a serialization stream has an header, which is the object ID itself, the type ID, and then the primitive fields or reference IDs. And basically it should be enough to inline the internal date or the internal timestamp value of a date into this record, and then you can restore this data and probably have a third of the data, and you save 60%, and in the long run it's a huge amount if the class is used heavily. So how can it be done? Simple ways to do that. If you own the code, you don't have to, you can write the code directly into your type if you like to do so. It's a convenience API which creates the type handler in the back. The only thing you have to define are the type itself and binary fields which convert data into primitive values. And every field has, of course, a name and 2 functions. One extracts the value and the other one puts the value back into the object from a binary representation, and that's it. You always have a field which is converted to a primitive and back, and then you have your type handler defined. That's easy to do if you own the code, of course. If you want to optimize the serialization for external classes, for example, if you're using images, let's say the buffered image in a JDK, you can't write code into the buffered image class, of course, because it's in a JDK, so you have to register an external type handler, just create a new class. And we provide a lot of base classes for custom type handlers. Just say what type you want to customize and what date or what primitive format should be extracted. In our case, a byte array, because we want to encode the image as a PNG and restore the image out of this data. Here in a store method, you'll see we just have to store the bytes into our binary instance. If you look at the store method, the binary container has to be filled with the serialized data. The buffered image itself is the instance, of course, we want to serialize, and we got the object ID and the persistent store handler where we can do the referential stuff, but most of the time it isn't needed. So we just have to store the bytes with our type on the object ID, and because we said we want to store our buffered image as a byte array, we create a byte array with just the image IO API, and that's it. And the restoring goes as well with the image IO. You get a byte array, you create a new buffered image, and you're good to go. So as you can see, it's easy to customize the serializer with custom type handlers. You can really bog down the amount of data which is created, and even we did it in projects. We have, for example, types which keep lists internally with linear data for time measurements. And what we did is we put all this linear data in one single record. So every time a lot of objects are loaded, the serializer or the storage engine has to do only one I/O operation and pull in a lot of data, and the type handler takes care of creating a lot of objects, and it can be has a heavy impact on performance actually if you combine objects in a single record. And if you want to do that, you can, but the default performance is basically enough for most application cases. But in this case, we had to optimize it for performance heavily. We're talking about microseconds. Then you can create or squeeze out the last microsecond out of the engine. So what do we do if our classes change? We can handle it with legacy type handlers. The example I said before, if you have simple changes, the engine will detect it. It's on a heuristic running internally. Or if you have more complex changes, of course, you can provide custom type handlers to do that. You can define how fields are moved, or even data is converted if you want to create an integer out of a string. Of course, you have to do a conversion. Or if you want to split up the name into first and last name, the engine doesn't know how you want to split it, so you have to provide a type handler for that. And it's very well documented. And there are several cases which are covered by the engine, so primitive type conversion can be done. If you want to make a long out of an int, the engine does it automatically because it can be done without data loss. But if you have complex conversions from string to two strings, engine doesn't know. You have to do it by yourself, of course. All right. One other thing we provide is object graph communication. So if you want to transfer data between two different JVMs, the object graphs can be serialized and updated, isolated through the deserialization and merged back into the original object graph, if you like so. And so you can keep two JVM states up to date, or can achieve a replication of some sort. The auto update of the graph, of course, is optional, and you can create object copies out of it as well if you need object copies for user sessions without interfering with the different user instances, depending on the use case, of course. It's in a model communication binary, and a simple example, on one side, of course, you have the non-dependent host. It works like with our storage engines. So there are foundation types which can be customized. So I bind it to an address and a port. You can, if you like, do a whitelisting to add another protection layer if you want. And the host channel acceptor is the entry point when a requests come in. So you can just receive the data, cast it to the type, and can send back an answer over the channel. It's a request response protocol like HTTP. A client looks like this, pretty simple. Connected to an address, register your types, create a client, and the client connects, opens a channel, and sends a request, and that's it. So it's a pretty simple API, which offers you a possibility for a simple transport layer. Of course, if you have an existing transport layer with different frameworks, you can use it as well. If you just want to send the stuff over REST with JAVAPRO or whatever framework you're using, you can put the binary stuff into the payload of the requests and do it by yourself. it's just a simple example of a transport layer if you don't have any in your project. So, if you want to look in the detail, the project is online at GitHub. Everything's open source. The docs are available at docs Microstream 1, and most of you probably heard by now, we are moving the code to the Eclipse Foundation. The Microstream project itself is split into 2 parts. The Eclipse Serializer will become a separate project, and the Eclipse store will be the part of the Microstream storage engine, which is based on a serializer, of course. We have it. The projects are live right now. These are the project sites at the foundation, the GitHub repos, and last week we released the first snapshots at the Maven Central, and the first documentation is online as well. Until the Eclipse store code will be up to date to the Microstream code, it will take until Q3, I think, because we isolated the code last year already, but the development moves right now to the Eclipse Foundation, and the active development is happening there. But the current stable release is still the last Microstream 8.1. So if you want to play around, of course, you can use the Eclipse libraries, but I'd recommend to stay at Microstream until the first final Eclipse release, of course. Yeah, the first snapshot is at the Maven Central or the Sonatype snapshot repository, and you can play around if you like. The coordinates look like that. It's the Eclipse prefix, of course. We have the serializer and the storage engine. All right, so we have a few minutes left for questions, if there are any. Yeah. Yeah. Yeah, the metadata model, which is generated before, uses reflection to analyze the classes. The generic type handlers have to do it because they don't know how the types you write look, so we have to analyze them. For the most common use types, like all collections in a JDK or local date or string and byte arrays and stuff like that, we have predefined types. Predefined type handlers, optimized type handlers, they don't use reflection anymore because they know how the types look internally. But for the generic handlers, we have to work with reflection. Yeah. It creates a few limitations, of course, because some stuff is restricted. Records is one thing. You have to hand over a flag to the JDK. It's in the documentation if you want to work with records. And on Android, the reflection is pretty limited because of security issues. In blackboxing, we had to circumvent that, but it still works like you want to. But yeah, there's no different way than reflection for that. Yeah. All right. Mm. Probably not. Yeah, if you don't open it for reflection, the engine can't handle it. One thing to do is you open the reflection for the Eclipse Serializer package, or you provide custom type handlers for that. Yeah. It's kind of different approach. Yeah, we didn't compare performance of it actually, because protobuf is not only Java specific, but it's more like a protocol specification. Our serialization format is open source as well, but if you I think it's done in one project. They have to follow a specific protocol. It's on protobuf, but a different one, I think Afro. They provide a special type handlers to create a byte format for a specific protocol. So you can do that as well, yeah. But there's no comparison of some sort with protobuf, no. All right, then thanks for joining and have fun on the last day of the JCON. See you.